Welcome back to ECE 220. This is the week for exam number 3. Exam number 3 is on Thursday, and it will cover, I don't even know what homework assignments, 7, 8, and 9, I believe. So this is op amps and inductors and capacitors. That's exam number 3. If you're in Group A, lab number 4 is probably not, well, I think it does have some op amps in it. So if you're in Group A, make sure you're attending your lab session number 4 this week. Homework 10, which is on subsequent material, RL and RC circuits, that's due tomorrow. And we have a couple of days immediately that you do not have to attend. You have to attend Thursday. That's the day of the exam. But Friday, the day after, we are not having class. And then a week from today is Veterans Day. So you won't be here in class next week at this time. Group B, though, in between all of those releases, will be needing to turn in your pre-lab for lab number 4 on Saturday. What I was hoping to do is work through some previous exams, and I thought I would just go from start to finish in hopes of seeing a majority of the material that you will be expected to be ready for on Thursday. Without any further ado, let's get started. I'm going to do this page by page, but the first one that we're working on is from 2018, a year ago, fall, exam number 3, and we'll start with the part 1 problems. And here, looking at this, obviously you're saying, okay, I need to remember how to combine inductors, but you want to start looking at maybe obvious simplifications. And the one that you would see, I hope, right away is that connection of those 2 points. And now you can put on your morphing goggles and you can hopefully now see that these 2 are in parallel, as are the next 2. And now we have A and B. Or we're now trying to look at the series combination of 2 parallel combinations. We have the parallel combination of 4 and 8, which inductors combine like resistors. And then we add that to the parallel combination of the second set. And now what do we have? We end up with 32 over 12 plus, let's say, now this is getting, so I'm just going to do it this way so that I can now have some cancellations, maybe. So that I now have 32 over 12 plus 22 over 3. And I could put those over a common denominator if I wanted to by multiplying by 4. And now I have 88 plus 32 over 12. And hopefully that now ends up being 88 and 30. Boy, this is terrible writing, isn't it? But you can follow along, I hope. This is now, I hope, 120 over 12. That looks like 1Z0, but that was 120. And now that's going to be 10. So hopefully I've done that correctly. Did everyone follow the logic of that? The key point is trying to see, are there any ways to simplify this before we get too deep into trying to combine and add things up. The other is, how do you combine inductors? They combine consistently form-wise as resistors. Parallel combinations of inductors are combined like parallel resistors. What about this mess? And I can say that I didn't create this exam, but mine might be even messier on Thursday, so be prepared. Again, you're looking for simplifications, and that's usually are certain points connected that will cause some simplification. Here, the one that you're wanting to focus on is that shorting, which now is shorting all of these out. So those two, that 6 and 12, you can essentially forget. Those are all now shorted out. So that now if you just sort of said, oh, that's just a node, now you have two capacitors, 1 and 3 in parallel, and you have another set of capacitors in parallel, and they're connected in series. And capacitors now are dual to resistors, which means that when we're combining capacitors in parallel, what do we do for them? They now are added together, and the series combination of capacitors we have to treat like we were combining those as we would be combining resistors in parallel. Or now we have a 4 microfarad in series with a 12 microfarad. And those now combine as if they were resistors, like we would combine resistors in parallel, so that now CAB is 4 times 12 over 4 plus 12, or 48 over 16. I haven't kept track of the units, but that's on the side. This is now 3 in the beginning units, which is microfarads, and that now tells us that is our answer, 3 microfarads. Now we're playing with dots. And the way that I do this is if I'm given one coil with a dot, then I work with that and I say, okay, here's a current coming in, that lead, and I try to wrap my fingers with the current and try to find where is the flux produced by that particular wrapping and direction of current. In this case, I'm seeing that we're now going in that direction. I guess if we use our imagination, that's clockwise. So now we have a clockwise direction of phi. And now I need to look at the other 2 coils, not necessarily all 4 leads of those remaining wires, but just one coil and a second coil, and see which way is the flux. Is it impeding or helping the way that the flux is going here in the first case? Which one do you want to look at? 1, 2, 3, or 4? Only need to look at 2 of them. I might just start working my way around and say, okay, let me look at 1. And now I put my fingers in the direction of that wire and say, okay, I'm going to say the current is flowing that way. And if I wrap my fingers around that coil, I see that that's now helping the flux. So in this case, I would say that's going to have a dot on that particular terminal. And now if I'm working my way around, I would say, okay, let me just go to 4 next. I don't need to worry about 2. I've already figured out the dot on that first coil that wasn't dotted. I look at the next coil, the last coil, and I say, okay, let me just assume I have current going in here. Now I wrap my fingers around that, and this looks like I have that phi going in that direction, so I would dot the other coil. And do I have an answer that says 1 and 3? That's what I would answer. Which LED is on? All of our LEDs have to be on Thursday, right? They all have to be burning brightly. All of our bulbs in between the ears have to be on. But now, this is kind of a mess in terms of looking, but there's no feedback, which means that, so this is now we really just have to worry about what happens when this particular op amp is in saturation. It goes to one of the rails. It goes to the positive supply rail or the negative supply rail. And here, in looking at these previous exams with students before today, it could be a little bit confusing, but I think the notation has been that the power supply pin on the top is traditionally V+. Although if you looked at this in PSpice, this, I think, is an inverted op amp, and so the negative supply pin is probably consistent with the negative the inverting pin on the op amp. Don't let that confuse you. Just assume that they are powering the op amp consistent with how it needs to be powered. Here, this one is now V-. That's the negative pin, and that's at the common point. And the V+ is now at 5 volts. That's now going to establish this op amp in a functional manner. It now can function, this op amp. And now what we're looking for, what's going to cause this op amp to be at the positive supply rail? What conditions will need to be true? For V0, the output pin on that op amp, what's going to take it to be at 5 volts? It's going to be at the power, let's just say, what's it going to take to get it to 5 volts? What condition? It's in saturation. There's no feedback. What has to happen for that output pin to be at 5 and not at 0? What relationship? It's all associated with the input pins. Remember, an ideal op-amp is some huge number, A, 10,000 or more, times Vp minus Vn. The non-inverting lead minus the inverting lead times 100,000. Meaning, if the positive input, or if the non-inverting input pin is more positive than the inverting input pin, this is going to go to the positive supply rail. If Vp minus Vn is negative, it's going to go to the negative supply, which in this case is 0 volts. That's what we're looking for. We're really trying to find what's Vp and what's Vn. Let's compare them and then see what the output pin is going to be stuck at. What's Vp? This one has a current source going to it, and we know that there's no current in that lead to the non-inverting pin. I can't draw it very well, so I just dotted it. There's no current flowing on that wire. That means all of this current is flowing through those two resistors. You can now figure out what this Vp is by Ohm's law. That's 5 milli times 1K. And the M and the K cancel. Vp is now 5 volts. What is Vn? That's this node. It's now being determined by a voltage supply connected through some resistors. And again, we have no current flowing there. Vn is now just a voltage divider relationship away from that 5 volt supply. It's now 1K over 1K plus 1K times 5, or we're just taking half of 5. V sub n is now 2.5 volts. What we now need to do is look at Vp minus Vn and figure out what its sign is, S-I-G-N. This is now 5 minus 2.5, which is bigger than 0, which means that VO, the output, goes to V plus. Because of no feedback, we are in saturation. We now know that this point, how many colors do I have? Not very many. We know that point is now 5 volts. This is now V0. Have a lot of 5s going around. Now what you want to do is you want to say, is that diode, light emitting diode, is that LED forward biased? Is it going to turn on? And let's just kind of agree that to forward bias a diode, it needs to be supply, or a voltage difference is 2 volts across it, at least. How much voltage is dropped across diode 2? 5 to common, 5 volts. 2 is on because of the direction of that diode. It's trying to forward bias it. You need the unhorizontal lined pin, the positive pin, to be higher in voltage than the lower. What about diode 1? Its positive pin, if no current was flowing, is 10, and its bottom pin is 5. It's positively or forward biased as well. 1 is also on. Both diodes are on. I hope the answer is C. That's how you try to work. What if, shouldn't be doing this, what if it was in the other saturation mode? What if V sub P and V sub N were just reversed for whatever reason? Let's say we connected up the input pins to where V sub N was 5 and V sub P was 2.5. What would the output be? What would V sub 0 be? If this difference was negative, V sub P minus V sub N is now negative. It's going to go to 0. It's going to go to the negative supply rail. In this case, that's 0. Which LED would be on, or would any of the LEDs be on, if the output is at 0? 1 or 2? I'll ask for your answer in 3 counts. 1, 2, 3. One little finger, right? 1's on, 2 is not, is it? 2 is between 0 and 0. You should, if you see these problems, whoops, no more problems, I'm done. Whoops, I can't leave yet. I still have most of the exam to go. Okay. So I'm a quarter of the way through, but point-wise, I'm less than that, half of that. Assume the circuit is in steady state. How much energy is stored in the capacitor? You have to remember the energy storage formulas. Here, the energy for a capacitor is 1/2 CV squared. Can we find in steady state the voltage across that capacitor? We're really looking for this voltage. And in steady state, this opens up, and all of that current is going through that 3K ohm resistor. That means that V is now going to be this 2 milli times 3K. And the M and the K are conveniently selected. They cancel, and we now have 6 volts in steady state across that capacitor. Or now the energy is 1/2, and C is 10 micro, and V we said was 6. So that now we have 36 over 2 times 10 micron. Or we now have 180 microjoules. Now we have an inductor. And we want to know, oh, this is at a specific point in time. And with this inductor, now we want to utilize Eli, which says, Eli says V sub L is L di sub L dt, and we need to find V. So this is now just a straight application of Eli. We now need to differentiate the current. The current is what we're given, that source current. We need to differentiate it, multiply it or scale it by L, and evaluate it at 1 millisecond. We differentiate I, and the 1's a constant. That's not going to impact the answer. We have minus a minus 1,000 e to the minus 1,000 t, and t is 1 millisecond, or 10 to the minus 3. So this ends up being 1,000 e to the minus 1. And we now need to scale that by 4 milli, or V sub L at 0.001 is now L, which is 4m times 1,000 e to the minus 1, or that's 4e to the minus 1. The m and the 1,000 cancel. E to the minus 1 is 0.37. 1.47. Problem 7. Find V naught. We're trying to find this value, and we're not even given a resistance value at the output. That must not matter. What's the first thing we probably want to look at? Do we have negative feedback? And we do, because the output is connected back to the inverting pin. We do have negative feedback. This now says, oh, well then you can assume initially that Vp is equal to Vn. With negative feedback, that tries to enforce the two input pins to be equal. What's Vp? Can we determine that? That's connected directly to 0, so now we're assuming that V sub p is equal to V sub n is 0 volts. We'll have to go back and check that. If we end up finding that in this configuration the pins are now trying to drive this system beyond the supply rails, then we're in saturation and V sub p is no longer equal to V sub n. That's why I'm saying negative feedback implies assume Vp equal Vn. Let's continue, see what happens. At the end, when we find V0, we'll check it to see if it's outside of plus 5 or minus 5. We now are assuming V sub p and V sub n are equal. It's 0. Let's apply KCL. That's kind of the next logical step if possible. Let's apply KCL at Vn. And I'm going to just go ahead and try to do it in as many variables, well, show you where all of this equation is coming from. So V sub n minus 1 over 500. That's this current. Plus that current, which is V sub n minus V sub o over 3K. And those sum to 0 because this current in that branch is 0. Going into the input pins on an op-amp is 0. We now know that V sub n, we're assuming, is 0. Now, however you want to do this, you can say, okay, let's now put one of those on the other side, or however we want to work it. We now see that V sub 0 is equal to minus 3K over, let's say, 0.5K. So that the K's can cancel. And V sub 0 with this assumption is minus 6. Alarm bells now need to go off because this is not, it's outside of our supply rails. This now says we have saturated, and for that reason, what is V sub 0 truly going to be? Can't go all the way to minus 6. It can only go as far as the supply rail, which is minus 5. V sub 0 is now minus 5 volts for that particular problem. If the problem would have asked for V sub n, we would have to go back and recalculate V sub n based on V sub 0 not being minus 6, but being minus 5. We would have to go back and put in variables for v sub n. Now all bets are off relative to v sub n and v sub p. They're not equal, and you'll have to then back calculate for v sub n if it had asked for v sub n. Whoops. Page 4. How many pages do we have? Quite a few more. We need to, I guess, hustle it up. Given v sub 0 is 100 volts and I of t is this exponential, find the final value of the voltage across that capacitor. And let me just remark that you need to pay attention to the way they've labeled things polarity-wise. This is not how I would label voltage across that capacitor with the current going in the direction it's going. So things are probably going to be counter to what I would have thought. Pay attention to polarity. I would probably say I'm going to just do this in the passive sign convention with the current coming into the positive terminal. I'm just going to work with v sub c, and then I know that v sub c is minus v. That's probably, instead of trying to chase my way around, oh gosh, I've got to remember that polarity is not the right one. Now what else do we need? Now we need ice, since we're dealing with a capacitor. I sub c is c dv sub c dt. And now we're asked for the voltage and not the current. We now need to invert this relationship. We now need to integrate both sides, or we now have the integral of dv sub c is 1 over c integral of I sub c. Let me just say we'll change this to having lambda for our variable of integration, d lambda. And this is going to go from our initial time, which is lambda equals 0 and lambda equal infinity. And this is now v at 0, and this is v at infinity. Or we now know v of infinity minus v of 0 is equal to 1 over c, the integral of I sub c, which is now 3 divide by minus 4, e to the minus 4t, and I need to remember that I'm doing milliamps, but I'm now going from 0 to infinity, and the units I'll just kind of keep on the side and realize that that has its own units, which is micro. Wake me up if I'm doing something wrong. V sub 0, O. And all of these are V sub C, not the V. I'm playing with V sub C. I'll back out how that's related to V at the very end, because otherwise I'm going to get confused. I evaluate this. Oh, what is V sub C of 0? In my terminology, it's minus 100. Because my V sub C is just the opposite of the way they've labeled V. Meaning here, that's now minus 100. And on the right-hand side, I now have 1 over whatever C was, 3 times 10 to the minus 6. Here's a 3, and then I have a minus 1/4. This is the 3 from there. That looked like an exponent, but and I now have e to the minus infinity minus e to the 0 milli. The 3's cancel. There's a 1. And what do I end up with? I end up with this minus 6 coming upstairs as a plus 6, so I have 1,000 divided by 4, and these minus signs work together to give me a positive value. So I now have v sub c at infinity minus a minus 100 equaling 250. Or v sub c at 1,000 is 250 minus 100, or 150 volts. But remember, this was asking for v, which was minus how I'd define my v sub c. That's now the answer that I'm looking for. I'm going to just keep going unless I see hands. Is that okay? I'm running out of time. Find v sub n. Now I am going to need to find v sub n. But what's the very first thing you want to think about in op amps? Negative feedback. If I don't have negative feedback, I'm saturating. If I'm saturating, then I'm just worried about the difference between v sub p and v sub n. In this case, I have negative feedback. That allows me to assume, and again, I might have to go back and change that, but right now I'm working under the assumption that v sub p is equal to v sub n. And v sub p is nice here. It's given us 2.5 volts. And now I'm trying to find v sub n. Probably not a good idea, because you need to make sure and check, am I in saturation or not? So let's now follow that through. Let's find v naught. And if it's outside the power rails, then we have to go back and back out what the inverting pin voltage actually is. Do you see? And this is in part 2, so it shouldn't be that easy, right? To just say, oh, that's 2.5. Could be. Might not be. So let's figure out what the output voltage is. Let's do the next step in our analysis, which is KCL at v sub n. And here is v sub 0. You can do this all sorts of ways. You could find the current through here, and then that's the same, but let me just do it this way. I don't even think I did it this way before. So now we have v sub n minus 0 over 1k. That's this one. Plus that one, which is v sub n minus v sub 0 over 3k, is equal to 0. Those are the only two non-zero currents, because this current doesn't exist. There's no current in the ideal. There's no current ideally going into the inverting or non-inverting pins of our op amp. We can now multiply through by 3k and say we have 3Vn plus Vn minus V0 is equal to 0. Or V0 is now 4Vn. Vn we said under the original assumption was 2.5, that's 10. And now we look back and we say, let's compare this to those pins. Alarm, alarm, alarm. So in fact, V0 is what? It's saturated as close to 10 as it can be, but that's 8. So now it's 8. Now we have to go back and redo our KCl to find V sub n. We now do V sub n minus 0 over 1k plus V sub n minus V sub 0 over 3k is equal to 0. You could go back and use the same. We're going to see it's the same. But now what do we know? We now know we have 3 V sub n plus V sub n minus V sub 0 is equal to 0. And this time we know V sub n, or I'm sorry, V sub 0. V sub n is now 2 and not 2.5. So V sub n is not equal to V sub p because this guy saturated. Is 2 an answer? Page 6. Find I sub 0. How many more of these do I have? Really? Okay. So here what you want to make sure of is I sub 0 could be different than the current going through the output resistor 10K and the feedback. We have to do KCl. This op amp is going to give us as much current as we need unless things are saturated. So I sub 0, eventually we're going to have to do KCl. But what's the first thing we want to do here? Negative feedback. Then we can apply KCl here, but this now says that V sub p is equal to V sub n. What's V sub p? It's right there. It's a voltage divider away from 5, and it's 2 over 5 divided by, or times 5. It's 2 volts. I'm speeding up a little. V sub p is 2 by a voltage divider. We now know this 1 milliamp, though, is not going in here, is it? So we have this 1 milliamp there. 1 milliamp is going through that 2K ohm in the feedback path. That allows us to actually find this voltage, V0, because we know this, we're assuming, is at 2 volts. We can now, with Ohm's law, say that 2 volts minus V sub 0 over 2K is equal to 1 milli. Or 2 minus V sub 0 is 2m 2k. This is now 4. Or V sub 0 is now, where did that come from? Speed. Hurried, rushed. It was 1 milliamp times 2. This is now 2 volts. V sub 0 is 0 volts. If I have 0 volts here, what's this current? 0. Whoops, that's not I0. Let's call this I1. So now we can do KCl at the output, and we now know that this I1 is equal to I0 plus 1 milli. And we can solve that for I0. This we found to be 0. I sub 0 is minus 1 milliamp. Page 7. I'm already on page 9 on my notes. All right, write a KVL equation. And this one tells you which mesh. This says for the top mesh. If they don't give you that information, I would just start looking for commonalities. And usually most of these expressions are correct. They just vary in the signs of these mutual inductance. So here's the top mesh. Can I just find the mutual inductance voltage and then move on to the next one for this? We have coupling from this coil to that coil. This current is I. This current is I sub 2. And this current is I sub 1. I now want to figure out what's the polarity on, well, if I'm doing the top mesh, is it clear that the voltage, the self-induced voltage, is 5 di1 dt with a plus sign? This is the self-induced voltage. Because that's the way the current's going. We'll just say, forget the dot. The dot is only an issue with the coupling, the mutual inductance. Now let's figure out what it's doing. Let's assume that the current going through the bottom coil is positive down, meaning let's look at I minus I sub 2. That's entering the dot. That means that we need to put a plus on the dot here, and now that's the polarity of the mutually induced voltage going around clockwise in that top mesh. Meaning I would now say minus whatever the mutual was, which was 2 d by dt of I minus I sub 2. And if I compare that somewhere, hopefully I see that is A. Saying this 5 there and this minus 2 there. The other terms better work out. They're all the same. Page 8. Find V sub 0. What do we know? Well, do we have negative feedback? Yes. So now V sub P is equal to V sub N is what we're assuming. What's V sub P? We can find it very easily because it's just Ohm's law away from that current supply and that resistor. V sub P is now 14 volts. 7 times 2, taking account of the units. What else? Oh, now we have this troublemaker. We have a T configuration in the feedback path. So we may not be able to, and what do we know? We know this is now V sub N. And we know this is V sub N. So we could find this current. Once we find that current, we know this current. We can find this current from V sub N divided by whatever that 1 k ohm was. Now we know this current. We can use Ohm's law to find V sub 0. Is that what we were asked to find? I found it. It was 25. But did you understand the logic? It was quick. You can find, you have this point as 35, and this is V sub N. So you can find this current right there. That current is the same as that current. You can now find this current because V sub N is this same point. V sub N over 1K is that current. Now you can do KCL here to find this current. KCL now allows you, once you have this current, you can use Ohm's law Because you know Vn, you can calculate V0. Because I is equal to the drop across there. Negative feedback. Yes or no? Yes. What's V sub P? There's no drop across that 5K, so this is now 5. We now know this in the assumption. This is now V sub N. You can now find this current and that current and this current to actually find this voltage V sub 0. That's the only unknown in your KCl equation. Once you have V sub 0, you can calculate I. But when you're calculating I, quit. Stop. How do I get it off of there? I get it. Where was I? Oh, once you calculate this, you want to check to make sure that it doesn't exceed those. If it does, then you have to go back and use that for your output voltage and then calculate your current based on that. One more, don't I? So this one, you can calculate M, and you just need to find your dots. Here's a dot, let's say, and then where's the other dot? It needs to support this flux. Isn't it this one? So now the dot would be plus and minus there by the mutual, and V is now the negative M di dt, where I is this. And I think if you go through that, you end up with 500. Hurried, but you'll be a lot better. You'll be calm. You'll be breathing. Hopefully that was helpful. We'll pick up at that point, not here, but on Thursday.